and kind of get started. So hi everybody, thank you for joining for today's Spotlight Series. For those that are tuning in for the first time, the Spotlight Series is a chance for our residents here at Autodesk Technology Centers to share the work they've been doing with our community. It's also a great chance for you all to learn about new and innovative projects, but ask questions of these presenters if you want any more information. For this week's format, we're going to be trying something a little bit new. This presentation is only going to be 30 minutes long. And if you have questions, please use the Q&A function at the bottom of the Zoom menu. We'll take those questions after the meeting and actually post them in the Tech Center Slack channel where Dr. Zoe and the team are going to answer these questions afterwards. And this is really to be considered of some of the teams that we have now that are remote and not in the same time zone. So for today's presentation, we're excited to have Ambots present. Ambots envisions a new form of smart factory that's powered by swarm manufacturing. So this is where thousands of mobile manufacturing robotics move freely across a factory floor, and they work cooperatively to actually finish production jobs. So from here, I'm going to pass it off to Dr. Wenchao Zhou, who's the Associate Professor of Mechanical Engineering at the University of Arkansas, and is also the co-founder of Ambots. Dr. Zhou.
Hello, everyone. Thank you very much for the introduction, and thank everyone for coming, and thank Autodesk for providing this opportunity. Today, we want to share an idea that we've been working on, swarm manufacturing. This project has been funded by the National Science Foundation, the Arkansas Economic Development Commission, the University of Arkansas, and Ambots. So if I look back the history of manufacturing technology, we'll notice that we're battling to serve two fundamental human needs. One is the product variety, and the other one is product volume. And because we want customized products for ourselves, this is why we need more variety. And we also want high volume because we want to be able to serve more people. And in the early days, the production is mainly performed by craftsmen using general purpose tools. For example, we go to a tailor for our clothes, we go to shoemaker for making our shoes. And when we start to be able to harness the power of steam engine, electric power, without having been constrained by the hydraulic wind energy provided by nature, we're able to set up factories offshore and being able to set up dedicated production lines for specific products. So this requires very high volume to be profitable. And therefore, we are entering an age of mass production where everyone was forced to use the same kind of products. And Henry Ford once famously said, any customer can have a car painted any color that he wants, as long as it's black. So that says a lot about the age of mass production. But we're not satisfied by this production capability because we want to be different. We're individuals driven by our individuality. Therefore, the flexible manufacturing lines are then introduced to make more variety of products to serve different types of customers who want different things. And of course, at a slight sacrifice of high cost. The direction that we're going eventually is to have a product customized to our personal taste. With the digital and personal production technology, such as 3D printing, hopefully we'll be able to make that affordable as well. As you can see on this graph, we're almost coming in a full cycle, except this time, we're gonna be able to make customized products and in the meantime, make that affordable. So to achieve the goal, there has been a lot of efforts in the past decade that has been devoted into the concept of Industry 4.0 since it was first proposed in 2011. And one of the goals is to digitize manufacturing by connecting manufacturing equipment to computers and the internet. This is essentially the application of concept of plus computing and plus internet, which has already been applied in many aspects of our life, such as e-commerce, movie, etc., etc. So everything can plus computing and internet. This is essentially manufacturing plus computing and internet. One problem is that the modern manufacturing, even with computing and the internet, is still largely based on Henry Ford's philosophy of assembly line, which was first implemented in 1913, over 100 years ago. And although the modern equipment such as robots and computers are used, but it's still largely organized in this 1D format. And the raw materials are processed sequentially, step by step, into the final product. There are several limitations of this type of line format. The first one is that although it can be automated for particular tasks, it's hard to achieve autonomy for a long time due to the rigid configurations that was set up for certain purposes. When the purpose changes, you need to reconfigure it, which is the reconfigurability issue. Typically after reconfiguration, you also need to recalibrate the machines for a different purpose, and all this manual work. So just like this year when Ford was asked to produce ventilators under the Defense Production Act, and they had to reconfigure their factory and recalibrate their machines, which took days and weeks to get a factory ready to produce for a different purpose. So although each machine and a component can be designed fairly modular, but it will be difficult to modularize the entire factory. And because they're organized in this line format, if one component or one machine that breaks down on this line, and this whole line is going to have to go down, and which causes robustness issues. In addition, the production line is typically designed to make products of a certain size and a certain weight, and also at a certain production capacity. These are all pre-designed. And it's very difficult to change the scale of the product and to change the scale of the production capacity very easily. So, and moreover, this cooperation between the machines are mostly sequential because each machine is staying in their own box, and there's a very little cooperation in parallel. So these are some of the issues with existing production paradigms, even with the aim of driving towards Industry 4.0 to plus internet and plus computing. To address these limitations, we turn our eye to Mother Nature. And this video shows a swarm of wasps building a nest together. They're actually doing 3D printing. It's just not in the way that we imagine though. But they're doing it together in parallel. And this would have been a much more natural way of production, like just how we did, over 1,000 years by humans manually. If somehow we can mimic these, actions of these wasps with robots, we can actually find some examples already in the industry. And this is how Amazon is managing a warehouse today. And instead of using traditional conveyor belts, and they're using a swarm of robots of high efficiency, low cost, and more robustness. And this is although this is not manufacturing, which is a more complex task due to consideration of materials, geometry, precision, and other complexities involved. And this is another example. This is a British company called Ocado, and they are using many robots to automatically pick up groceries, to automate grocery shopping, which increases the efficiency so that you don't have to pick up these groceries yourself. So with these inspirations from Mother Nature and other industries, we thought it would be a good idea to apply it to manufacturing, and hence swarm manufacturing. And this is a visualization of the idea that we came up with. A swarm of mobile manufacturing robots freely move on a 2D factory floor, transforming a production line to a production floor to reconfigure and work on different production jobs like this. And compared to the modern production lines based on Henry Ford's philosophy, this idea literally brings manufacturing into a new dimension, from 1D to 2D. Manufacturing can be done by establishing a computational scheme to mimic how nature handles production, and then embody this computational scheme with manufacturing robots. Compared to the plus computing or plus concept we just mentioned, and this can be dubbed as computing plus, which is centering around computing and the intellect. So you start with computing and embody that computing with reality, with robots. So it has many advantages. First of all, with the advancement of AI, long-term autonomy of the factory becomes possible because the robots can reconfigure in real time for different purposes. Purpose, you can always change the configuration of robots, and they can do it automatically in real time. And after reconfiguration, these robots will be able to dynamically auto-calibrate after reconfiguration, and thereby changing the production configuration in minutes instead of days, like what Ford did this summer to produce ventilators. So both the robots and the factory can be modular, because you have many robots. When you have breakdown of one robot, it's not going to affect others. It's going to be fairly robust. You can have other robots to drag it out and to continue the production without interruption. And also the factory can be easily scaled up to produce objects at different sizes, at different weight, and also at different capacity. If you want to produce one, you only increase it to 10, to 100, you can do that by simply adding more robots. And it's very flexible for scaling up. And in addition to that, the robots can cooperate with each other, and they can work in parallel to speed up, like this, so that which essentially reduces the manufacturing costs because time is money. So this is a demo of this concept. We have chosen 3D printing robots to start because it is a very well digitized manufacturing process, and it is relatively cheap to build and flexible. And also my background was in 3D printing. So this is the first fully functional prototype that we built to demonstrate the concept of swarm manufacturing or swarm 3D printing in this case, because it only has 3D printing robots in this platform. And as you can see, two mobile 3D printing robots are printing together to print an object that's larger than themselves. This was about 1.5 years ago, and this demo video was very well received on the internet, receiving an estimate over 400,000 views on different social media platforms. If you haven't seen it before, here you are. And to expand the platform, we also want to be able to support different materials with different types of print heads. Other than these regular thermoplastics that can be printed using in regular extruder, we're also working on print heads that can support printing of the liquid resin and the ballistic gel material. So this is the print head that we developed to print the liquid resins. Unlike the stereolithography that you use, for example, in Formlabs machines that use a laser to scan to cure the liquid resin, it uses an extruder to deposit liquid resins and use UV light to cure it, and which makes this whole process compatible with the Swarm 3D printing platform, because you need a printer head that can deposit materials And this is the printhead we developed to print a type of ballistic gel, which is a soft gel that has many good properties that can be used in many different applications. First of all, it can resemble tissues. It can be made as hard as your bone and as soft as the skin by changing the recipe, essentially the concentration of water in the recipe. Which can be potentially used for bio applications, such as pre-surgical planning, medical training, etc., to make these cadets for these purposes. Second, it's transparent, and it has very good optical properties. And we've tested, it actually has a higher transmission rate than glass. So if you use this for optical purposes, it will perform better in a visible range light, in a visible light range. So we can use it to produce, optical circuits like splitter and combiners, as like this. It's a flexible optical circuits in 3D on a curved surface. And then we can also use it to make waveguides like this. This is the lab logo, AM3 lab. And you can also print 3D structures and make different kind of quadratic patterns, which also has some interesting applications. So we're also developing a printhead that can lay down, continuous carbon fiber. And this is still a work in progress, but we're hoping to be able to integrate this printhead such that the swarm will have the capability to print a continuous carbon fiber. In addition to different types of material deposition printheads, we've also developed a pick and place printhead for digital assembly. So this is a demonstration of how a gripper can be used to automatically perform digital assembly operations, which can be used to integrate components that cannot be 3D printed. For example, electronic components like this LED name tag here. So in addition to the hardware robots, another challenge in swarm manufacturing is the discretization of a continuous manufacturing planning for the execution. For swarm 3D printing, we developed a discretization method by splitting a digital model into smaller chunks like this. We call it chunking, and which allows robots to work together on different chunks without colliding into each other or the materials that has already been printed. So one immediate question for this chunking method is how will the chunk bound affect the strength of the printed parts? So we did some tests with PLA by comparing to standard 3D printing parts that has not been chunked. And as we can see here, we vary 3 different chunking parameters, including the slope angle of the chunk and the chunk overlapping, and also the number of shells at the chunk bound. And by controlling these 3 parameters, we test against the standard reference part, which is here. And we can say we can find parameter combinations to get properties at least comparable or sometimes even better to the standard 3D printing part. And we also did some micro CT scanning that shows the density at the chunk bound is actually higher than the rest of the part. And although additional study will be needed to evaluate other materials and better understand the chunk bound strength, these preliminary results show good promise of this discretization method. So for 2 robots, like what you saw in the planning can be relatively easy, but for many robots, and the complexity goes up very quickly. So we developed a mathematical framework to describe the problem of scaling in terms of dependency relationships, geometric constraints, and resource constraints, such as the number of robots that you have. So these 3 different things represent the time and logical constraints respectively. So which helps us define this whole problem. And based on these constraints, we developed a heuristic strategy for scheduling many robots without conflicts. And this shows 4 robots printing a large rectangular bar, which has been divided into 20 chunks. And the dependency tree like this can be constructed to guide the robots to print in sequence and also in parallel without conflicts. And the chunks on each row can be printed at the same time without problem. So this is the simulation and validation of this scaling strategy, showing 16 robots working together to print the landscape of. And as you can see here, there's no conflict between the robots when they're printing different chunks. And the scaling is also quite good. We were able to achieve about 11 times speed up with 16 robots. So for a heterogeneous swarm, consisting of different types of robots, the scheduling can be even trickier. And we haven't done too much work on it yet, but this is a preliminary demonstration of how 2 different types of robots can work together. And it shows 2 printers and 1 pick and place robot to print a frame and with an embedded step motor. So with all this, one thing that we've realized about the mobile manufacturing robot is that they don't actually have to be mobile. They just need to be able to move to different locations on the floor automatically. So we separated these mobile platforms with the arm, the robots, for 3 different reasons. First of all, the mobile platform can be reused, for different arms, so that they don't have to sit idling during the printing process, because the printing is actually taking a lot of time. This will reduce cost. And secondly, it gives the arm more room of motion, because when the mobile platform sits underneath the arm, it actually blocks some part of the space. And the third and most importantly, stationary robots have already been widely used in factories. So using stationary robots will reduce the barrier for adoption. So this demo shows how this new platform can work. And they printed a 1 meter by 350 meter honeycomb structure. And this is a structure, and that's printed by the platform, and that's holding by our co-founder, Austin Williams, as you can see from the picture. So this is the design of and the implementation of the platform. On the left is the design, and right is the implementation. It consists of 4 floor towers. Each is 600 by 600 millimeter. And the mobile platform is battery powered, and it can carry the robot arms between different locations while maintaining continuous power. The robots get power from the floor while printing during the printing process. After the mobile platform idling for 5 minutes, you will automatically go back to this charging station to charge its battery. So this is a visualization of the next iteration of the platform we want to build, essentially to expand on this concept with more robots, more mobile platform, and more floor tiles, and be able to print larger objects like this Chicago city. So we have been trying to commercialize this idea too. One of the initial target market for commercialization is in the architectural precast construction industry. So the final product looked like this. It's essentially the walls with all these different kinds, beautiful patterns. They're concrete, and then they're made with concrete by pouring the concrete into a form like this, essentially a mold. And our targeted use case is essentially to print these forms, and which is a multi-billion-dollar market actually. And we have several competitive advantages over existing solutions, which I'm not going to go into details right now. So this is some of the technical milestones we want to achieve for the next steps. We're hoping to be able to release a beta-ready platform in early 2021, and an AM boards factory by 2025, which will consist of thousands of different manufacturing robots that can take orders from online and produce them autonomously. So we hope that we can, just like McDonald's, to franchise this AM boards factory model and build a network of thousands of these AM boards factories around the globe, such that when someone places an order online, you can be routed to the nearest factory for printing and for fast delivery. So of course, with all the work are done by this great team that's listed here, and most of them are actually here today to answer any questions that you may have. And special thanks to our long-term collaborators from City Lab. So this idea actually has generated quite a bit of buzz around the world, and these are some of the notable reactions from the internet. And the ultimate goal of this swarm manufacturing concept is such that manufacturing can be done autonomously and with customized product and in an affordable way, satisfying the two basic human needs that we just mentioned with product customization and the product volume at affordable cost, as we presented in the very beginning, to complete a full circle. So thank you all again for coming, and we're here to answer any questions that you may have.
Fantastic. Thank you, Dr. Zhou. That is actually really exciting, and thanks for sharing all that work. We want to remind everybody, if you have any questions, feel free to leave them in the Q&A box or in the Tech Center Slack channel. You can leave questions there, and Dr. Zhou and his team at Ambots will be answering questions the rest of the day today and the rest of the week. So if you have any questions for them, please do reach out, and we'd love if you could take a quick minute to fill out that poll survey just so we get some feedback on how this new format went. Thank you all.